Alrighty, hi everyone. We'll get started. So thanks for the coming to the last minute review session. I wasn't sure if I was going to be able to make this, so thanks for staying flexible. Um, so as a reminder, your first exam is tomorrow during class time. So just show up to like regular lecture time, and then you'll just sit in a seat, take your exam, and then you can leave when you're done. Um, all multiple choice, same format as the practice exam, and you'll have the full lecture period to do the exam. Um, any questions for me about the exam in terms of like taking it, not necessarily content? Okay, cool. I'll take silence as a no. And then just throughout this Zoom session, if you have a question, you can feel free to use the chat, take yourself off of mute. I don't really mind either way. Alrighty, so this next hour will be for you to ask questions. So you can ask anything, practice exam, just general questions, anything you want to see to review before the exam tomorrow. Mhm. Okay, awesome. So for question 14, we said a given mass of gas occupies a volume of 4 liters at 6 degrees Celsius and 550 millimeters mercury. Which of the following mathematical expressions will yield its temperature at 200 or 2.50 liters and 900 millimeters of mercury? So what we're looking at here is a gas laws. And we're saying that a given mass occupies a volume, a temperature, and a pressure. And we're asked for its temperature at a given volume and a given pressure if we change the volume and pressure. So this is looking at the combined gas law. So we have P1 V1 over T1 equal to P2 V2 over T2. We are solving for temperature 2. So we're going to rearrange our equation. So we would have T2, I'll show the whole thing. It's T2 times P1 V1 over T1 equal to P2 V2. All right, then multiply T1 across. So then it's T2 P1 V1 P2 V2 T1. So then T2 is equal to P2 V2 times T1 divided by P1 V1. So then you're looking at the combinations of the given examples for what would yield that, right, you're looking for this in order to give T2. You have to note that temperature must be in Kelvin, so you can automatically get rid of A because that did not convert to Kelvin, that's still in Celsius. So temperature 1, I think this is T1, this is V2, oops. V2, this is pressure 2, 4 liters is volume 1, and 550 is pressure 1, so that looks like D. Does that make sense, Andrea? Right. Seth, are we looking for the density in that question from your homework? Okay. So from that one, right, we have density is in grams per liter, which is mass over volume. Right, that's what density breaks down into. And then we have our ideal gas law. So ideal behavior means that you can assume PV is equal to nRT and use Pivner, or the ideal gas law equation. And here is your moles. And we know that molar mass is equal to grams over moles. So you can rearrange, right? So this can be molar mass is equal to, I'm going to say M is mass over N moles. So we can rearrange this to say mass is equal to molar mass times N, right? Or then we can say moles is equal to mass over the molar mass. So we can plug that into PV is equal to nRT, mass times RT over molar mass. And then you can solve for volume, which is mass over volume, which here is little m over V. So you would get PV molar mass mRT. You want to divide by RT. And then you want to divide by volume. So you get pressure times the molar mass divided by RT is equal to mass over volume, which this is density. And so the molar mass that you use here is for the sulfur dioxide. So then you would just have to change your temperature into Kelvin, and then you have to solve for your molar mass, and that should give you mass over volume or density. Do you get? Yeah, and then you're given that equation, density is equal to molecular weight or molar mass times pressure, RT, on your exam. So you never have to derive that equation. That would be given to you for your exam tomorrow if you had to do something similar to that. And then for question 14, we used this equation here, but we just said that the number of moles or the mass was the same, right? If the mass is the same, that means the number of moles are the same. So we just removed that n component. So that's where P1V1 over T1 is equal to P2V2 over T2. So both of those are given to you for your exam. Does that help, Seth? Great. Okay. Okay, we'll do 8 and 7 since both of those just came in. So for question 8, we have if 15 milliliters of 1 molar HCl solution is mixed with 25 milliliters of 0.250 molar sodium hydroxide solution in a process that produces 273 milligrams of NaCl, what is the percent yield of NaCl? So what we're given here is we're given a volume and a concentration and a volume and a concentration of both of your reactants. If you're given a volume and concentration, or if you're given a concentration of both things for your reactants, what kind of problem is this first? Before it's an acid-base question, what is this? Before it's even a percent yield equation, what is this? Good, right? So this is a limiting reactant. Does anyone know what our ratio from acid to base is here? 1 to 1, 2 to 1, 2 to 2, 1 to 3, 9 to 7. What's our ratio of acid to base? So it's actually only 1 to 1. So if we were to solve, or if we were to balance this equation, we're looking at Cl and Cl is the same. Sodium and sodium is good. We have 1 oxygen, and then we have 2 hydrogens. So this is actually balanced. So this is just a 1 to 1 ratio. So that means that we just need to compare our number of moles for the HCl and for the sodium hydroxide. How do we get to moles from volume and concentration? Perfect. Yep. So molarity is moles over liter. So if we multiply our concentration by volume, then we should get moles. So we can say 1 mole times 0.015 liters, right? We do need to change that. We're going to have 0.015 moles of HCl. Sorry, you guys, my nose is running. Sorry. So we have 0.015 moles of HCl, and we have to do the same thing for our sodium hydroxide. So we have molar times 0.025 moles. Oops, not moles. 0.025 liters. So we have 0.0625 moles of NaOH. So which one's our limiting reactant? Sorry, I did bad math. And sodium hydroxide is the limiting reactant because we have 0.00625 and instead of 0.0125. So this is our limiting reactant. So since we only have that many moles of sodium hydroxide, we need to figure out how many grams of sodium chloride get produced from this many moles of sodium hydroxide. So in a 1 to 1, we're going to say for every 1 mole of NaOH, we have 1 mole of NaCl. And then we're going to say that 1 mole of NaCl is equal to 55. Is that what it is? 22.9. 58.44 grams. Oh, sorry, I did this again. So we end up with 0.365 grams of NaCl, which is 365 milligrams of NaCl. Okay. What is that 365? What is that called in terms of percent yield? Good, that's our theoretical yield. So in our percent yield formula, we have actual over theoretical. What we get from the limiting reagent is what we assume to be our theoretical yield, what we expect to see. So that's just going to be our theoretical yield. What is our actual yield? Yep, the one that is given, this is our actual. So in order to get percent yield, we're going to have actual, which is 273 over 365. And what do we get for that one? Is that 60%? 74. D. %74.8%. Okay, does that help out with my people that asked about question 8? Or so you can't just jump into percent yield. If you write the percent yield formula, then it's gonna be, it should say, oh, I only have my actual. Right? I need my theoretical. Where does my theoretical come from? And that comes from getting the limiting reagent. That's what you want to think about when you see those types of questions. Okay. And then let's talk about 7. Okay. So this is just a fancy way to ask a limiting reagent question. We have considered the chemical reaction tin. Is that tin? Yeah. Tin plus sodium hydroxide yields sodium tin oxide and hydrogen gas. How many moles of hydrogen are liberated from the complete reaction of that many kilograms of tin metal in excess of sodium hydroxide? So for this one, they're telling you what the limiting reagent is. They're telling you that you have excess sodium hydroxide, so all of your tin metal gets used up. So you're going to do 3.47 times 10 to the 4th kilograms of tin. We need to get into moles. Does anyone know what the molar mass of tin is? I don't know that one. Thanks. 118.7 grams. Right, what we notice is these are different, so you can just change the kilograms to grams immediately, or you can add a step where 1 kilogram is equal to 1,000 grams. Right, that's fine. Once we get to moles, we need our molar ratio. This reaction is not balanced, so we need 2 moles here. That gives me 2, 2, 2. Okay, that looks balanced to me. So even not balanced, this is going to work out fine. But for every 1 mole of tin, we have 1 mole of hydrogen. And then that should get us our number of moles of hydrogen. So I got D, 2.92 times 10 to the 5 moles of H2. Are we in agreement on that one? Does that help my number 7 question? I will take silence as a yes. Okay, can you explain mole fractions with partial pressure? Sure. So When we talk about mole fractions with partial pressure, we're looking at this equation here for our mole fraction related to partial pressure. Pressure comes from the number of collisions that the gas molecule is making with the container that that gas is being held in. So if you have more of that molecule or more of that compound, then the number of as the number of moles increases, the number of collisions that that molecule or that type of gas is going to create, creating a larger pressure. So as you increase the number of moles of something, you're going to increase the amount of pressure that that type of gas is exerting. So if you have mole fraction, which is, we'll say mole of gas A, then we're saying that that's equal to the number of moles of A that we have divided by the total number of moles in our system. So if we have moles of oxygen and we have moles of hydrogen, right? If we have 3 moles of oxygen and 2 moles of hydrogen, then we have 5 total moles and 3 moles are made up of the oxygen. So we have, right, 0.6 as our mole fraction for that one. That means if we had 100 millimeters of mercury of total pressure of that system, then 0.6 of that is coming from the oxygen. So that means that 60 millimeters of mercury of that pressure is coming from the oxygen molecules and 40 millimeters of mercury is from the hydrogen molecules. Okay, so that means that the number of moles is related to the pressure of that system. So if we had, right, I'll just write that out. I'll do it differently. If we had 7 moles of O2 and 3 moles H2, we now have 10 total moles of gas. And so the mole fraction for O2 is 7/10 or 0.7. And the mole fraction for H2 is 3/10 or 0.3. So if you have 100 millimeters of mercury total pressure, 70 millimeters of mercury is going to be from O2 and 30 is going to be from H2. Because we can say that 0.7 is equal to X over 100. So X would be 70 millimeters of mercury. And this 0.7 came from the mole fraction of oxygen. Does that make sense, Will? Cool. Okay, what other questions do we have? Anything else? We feel comfortable? Are we ready? Do we feel ready? Do we not feel ready? Okay, well, if no one's gonna ask a question, I'll give you some tips, I guess, for taking an exam. So, right, this is gonna be a multiple choice question. Nope, you'll be given the equation sheet. You can just use whatever the reference is for the mock exam. That'll be what you have for your exam as well. Seth, yes. Yep. So assume ideal behavior means PV is equal to nRT is viable for that question. Yep. Because PV equals nRT is the ideal gas law. So we're saying under ideal conditions, this is how a gas works. You cannot bring your own periodic table. You will be provided a periodic table that you can rip from the front of your exam. And it'll look like this periodic table. Probably not. Under not ideal conditions, the equation looks super wonky and super gross, so they probably won't ask you about it. I mean, I'm hoping not. That would kind of be kind of mean if they did. I don't think there was one on the practice exam if I remember correctly, so I wouldn't worry too much about it. It's a great question. So when do we use Avogadro's number? You're going to use Avogadro's number when you get questions like, how many molecules of this? How many atoms of this? You start off with this many atoms. How many moles exist, right? When you're talking about atoms and molecules, that's usually when you see, the use of Avogadro's number, right? Sometimes you're given a certain number of moles of hydrogen gas or a certain number of molecules of hydrogen gas, and you need to know how much that weighs. You need to get out of molecules, get that into moles using Avogadro's number, and then use molar mass um to get to the grams of that one. You don't need to remember some of the common molar masses because you can always find the molar mass from the periodic table. You do need to know your diatomic ions. Those are important. Let me let me So your diatomic elements are nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Does anyone see what number that makes with the highlight? Yep, so that makes a 7, but how many elements are in that? Right, there's 6. So I made a 7, but I only highlighted 6. This is telling me that these are 6 of the 7 diatomic molecules, but there's one more, and that one more is hydrogen. So you just need to remember that it's the hydrogen that is the 7th one. But if you know the corner as your 7, or that there should be at least 7, hopefully you remember that hydrogen is just the other diatomic molecule. So you can use your periodic table to your advantage there. Um, Acid bases chart. You will probably not be given an acid base chart. You will just have to recognize your strong acids and strong bases. Which is Yep, so you have your 6 strong acids and 6 strong bases. You just need to recognize those that they exist, but like in that number 8 equation, right? Number 8, yeah, number 8. Right, it said it had HCl and NaOH, so they just used a strong acid and a strong base. There is a way to figure out if it's strong or weak, but if you just know your 6 strong acids, you consider anything else weak. So you just need to know that 6 are strong. Everything else is weak. No, probably like 2 or 3, maybe, for acids and bases. Okay. So we have this question here. Oh, let me just move this. Down. Okay, so we have this question here where iron 3 and oxygen react, and that occurs at 25 degrees Celsius, 783 torr, and a volume of 23.4 liters. And what amount of iron in grams is needed to fully consume all of the oxygen? Okay, so a couple things we need to know about this reaction is that we have iron 3, which is going to be a solid because it's a metal, and we have O2 gas because oxygen is a gas in its elemental state. And those are going to react to form iron oxide. Oh God, iron 2O3. Right, those will form iron oxide. So then we need to balance this. This is a 2, this is a 3, this is a 4. And then we're saying that at 25 degrees Celsius, 783 torr, and a volume of 23.4 is what the reaction is happening at. This means that we can solve for the number of moles of oxygen because given PV is equal to nRT, we have temperature, we have pressure, and we have volume. We just don't know N. We don't know N here. So we can solve for that. Pressure, we have to change to ATM because our ideal gas constant is in that one, or is in ATM. And we need 25 degrees Celsius needs to go to Kelvin, which is 298 Kelvin. So for Pivnert, we have pressure of 1.03 atm times 23.4 liters divided by 298 Kelvin, and just so we know our gas constant. Perfect. 0.08201 liters times atm over moles Kelvin. Hugo, yes, usually finding the number of moles of the substance really is your first step. You can't really do a lot of chemistry unless you're in moles. So if you don't have moles, you should usually find a way to figure out how to get to moles. So this becomes this is just 2. So this is 0.985 moles of oxygen. So then that's how many moles of oxygen we have. We now need to use our molar ratio to get to moles of iron and then grams of iron. So using our balanced equation, we have 0.985 moles of O2. For every 3 moles of O2, we need 4 moles of iron. And then iron is 55.85. So 1 mole of iron is 55.85 moles or grams of iron, excuse me. It does not matter that it's a 3+ or just the solid because it's just change in electrons and those don't count towards the mass. So I got 73.4 grams of iron. So whoever asked that, hopefully that helps. Okay. Yeah, as long calculators are allowed as long as it's not connecting to the internet. Like this one is fine. And if you have a graphing calculator, that's fine as well. Just don't do things on the internet if your calculator can connect to the internet. Yes, that is the same for quizzes. Please do not connect to the internet on your calculator for a quiz. But you can use a graphing calculator for your quizzes. There should be about 17 questions, same as the practice exam for your exam tomorrow. I will tell you that it'll probably be similar to the practice exam, but under testing conditions, it will probably feel harder than the practice exam. Looking at both of them, I would say they're pretty similar. Working with Dr. Bengali, I would say they're pretty similar, but I feel like all students, once in the testing setting under a time crunch, blah, 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 nerves are racing. Students do feel to say that it is harder than the practice exam. But maybe in the back of your head, you're saying, no, this is similar, this is okay, and then you'll feel better about it. It'll be a similar breakdown to the practice exam. I would say probably mostly math. Maybe a couple conceptual questions, but mostly math because you have to use your concepts to apply the math. So we're checking both in the same question when we do that. The practice exam he put out in an announcement on Monday, the 10th. It should be linked there. You can download it as long as you are signed into your TAMU account. So for the strong bases, I figured out a way. So the strong bases are these guys right here. So you go 1, 2, 3 over down 1, 2, 3. Right, you just have to put an OH next to them. If you remember that this is a +1 and this is a +2, then you know that these only get 1 OH, etc. And then your second column gets 2 OHs because OH is a -1 polyatomic ion. So if you have a calcium that's a 2+, you need 2 of those to balance that out. So that's how you remember the bases. The strong acids, I don't really have a good trick for that one. Your strong acids are chlorine, bromine, iodine, right? HCl, HBr, HI. So if you remember those, that helps. Then you just need to memorize the 3 of HClO4, HNO3, and then H2SO4. So if you only have to memorize 3, that's not too bad, I think. Where's the formula sheet? You are given nitrate, chlorate, and sulfate on your solubility chart. So, right, you just need HNO3, HClO4, and H2SO4. I don't know. You can use that to your advantage as well for memorizing those. Oh, geez Louise. Right, and then there are the halides at the top, right? So they are all of the ions are technically on your solubility chart for acids, if you want to memorize it that way. Any other questions? Are we feeling good, medium, bad? You memorize acids and bases just so that you recognize which ones are strong. If you know which ones are strong from the acids and bases, then everything else is weak. So if you're doing an acid-base question and you don't see any of the acids or bases that are strong, then you know you have a strong acid and a weak base or something like that. I don't think you need to memorize any formulas. Most of or I think all of the formulas you need, honestly, except for maybe like M1V1 is equal to M2V2. I think other than that, that's really the formulas you need. It's more of knowing when to do certain operations, I guess I'll call it. but that comes from following units. So if you can follow your units and you can convert between units, that'll help you with your questions. In terms of like, oh, I need to get to grams. How do I get to grams from here? And you're in moles, right? Then you need to use your molar mass. Or you're looking at PV is equal to nRT and you're given grams, right? But you need to get to moles. How do you get to moles from the grams that you're given so that you can use PV is equal to nRT? Think of it more as a roadmap that way, unless like, oh, I need to memorize this equation. You need to understand what the question is asking so that you can perform the correct math. If they are weak, then they are still aqueous. But don't worry too much about weak acids, weak bases. Strong acids, strong bases are really what's most important. When you have a strong acid and strong base versus a weak acid and base, it just depends on like what your final products are in your net ionic equation. Um, that's really the only difference in like how much salt is produced and stuff. But we're mostly gonna ask you about strong acids and strong bases. Yes. So we'll do number 2 to show this one. So when we talk about spectator ions, right, we're looking at usually something that forms a precipitate or that solid. So we have PB, right? Anything that's aqueous is going to split. So these are all going to split. So we have PB2 plus into ClO3 minus plus K plus and Br minus going to PbBr2 solid and K plus and ClO3 minus. In our original equation, this needs a 2, which means this needs a 2. So this is a 2, this is a 2, this is a 2, this is a 2. So when we look at identifying our spectator ions, what we're looking for is things that look the same on both the left hand and right hand side of our chemical equation or that reaction arrow. So looking at 2K plus and 2ClO3 minus, both of those look exactly the same on the left and the right, right? We have 2ClO3 minus and we have 2ClO3 minus. So we're going to cancel those out. We're going to cancel out the 2K plus ions as well. Therefore, these are spectator ions because they're not doing anything. Once they are in solution, they just hang out and chill and causes a barrier to anything else that's going on in the reaction. The meat and potatoes of our reaction is coming from iron and bromine forming lead and bromine forming lead bromide. The spectator ions is what is just not doing any chemistry. It's literally just hanging out. It's being a spectator. So K plus is your ion here because this is not ClO3 minus. Right, it doesn't split from the lead. It's not a spectator ion because it's involved in the chemistry that's happening. It's part of our net ionic equation, which is showing us this is an important ion that we're looking at. Yep. Yes, for these types of questions, they will always say what the state is. And so you can't break a solid, liquid, or gas, but you can break an aqueous solution. Weak acids break apart in precipitation. Yep. So if you have like HF, right? This will still break apart into H plus and F minus. Yep, and same for Andrea, right? Strong acids and weak acids and bases, all of those break in solution for net ionic equations. Yep. What was that one, Hugo? This one? Okay. And this is recorded, so I will post this on my YouTube once it's done. If you need to go back and look at anything for today. Anything else we have questions on? Are we feeling better after this? Hopefully this is answering all your questions. Perfect. That's what I like to hear. For the next exam, I will not be out of the country beforehand. So I promise that I will do more to help you the week prior as well. It's linked in the resources and contacts. So if you go to Canvas, the home page, resources and contacts here, and then link to all review session recordings. If you click any of the recordings, those should bring you to my YouTube. And then, let's see. It looks like probably the 24th and 25th of September, were review sessions for the first exam for last semester. So if you want to go back and watch those, you are more than welcome to do that as well. It was the same course around about the same material, so you can look back at those. The 24th and 25th of September here. Any other questions for me? Hopefully this is like the last little bit of studying that you do. Make sure you get a good night's rest. Make sure you set an alarm. Make sure you eat a breakfast. Um, don't be cramming right before, right? Just briefly run through what's ever in your head. You know more than you think. And then once you get to the exam, take deep breaths. You're going to be okay. It's one exam, it's one question. If you don't know it, come back to it. Do the ones that you do know right away. And make sure you at least put an answer down for every question. If it's a multiple choice, you have a 25% chance of getting it right. If you can narrow it down or get rid of, right, some questions, you increase your chances. Right, use all your test taking strategies. We're testing you on 3 chapters, so use your exam to your advantage. Maybe there are some key aspects along the way that you can borrow from other ones in terms of concepts and stuff. Yep, all the questions are multiple choice. Anything else for me this evening? Not necessary to show your work. Seth, I think that they will tell you what the compound is. I don't think that we are necessarily asking you to memorize these. Um, So if you don't know them, raise your hand and we can try and help you out during the exam. But I think like if you look at your solubility chart, sometimes that pops up. So like ammonium is NH4 plus, so that means ammonia is NH3. So there's a little bit of stuff there. Yeah, Miriam, so if you go to Canvas, resources and contacts, and then link to all review sessions recordings. Any recording will bring you to my YouTube. And then I try to organize those into playlists from there so that you just find this year's stuff or this semester stuff and then last semester stuff if you need it. Yep. Anything else for me tonight? Okay, I will take silence as a no. Um, so with that, I'll kind of close it up for here. Again, make sure you sleep. Don't stay up too late. Rest is great for the brain. Um, email me if you have any questions in the meantime. I will hopefully get back to them before the exam. And yeah, good luck to everyone. I'll see you in class tomorrow. Good night, good luck. Sleep tight. Bye, y'all.